Hello. As I promised, I was going to walk through some of the solutions to the exercises that you were given in project for this class. And so the project for this, the section in particular of the course that I'm talking about is the one where we're dealing with raw data. I'm using raw loosely, of course, structured data. It's in an XLSX file. That was provided in the project description. We have 4 cases to model. In this aircraft underscore data XLSX file, you'll find a row for the Airbus A320neo. And the task here was to construct a BFO-conformant model reflecting the content of all of the columns. And so the preceding lecture I discussed, BFO and its theory, and you can tease out from that what conformance means, as well as construction or how to walk through design patterns when you're building BFO-conformant models. So hopefully that would be helpful for you as you work through this exercise. But I wanted to provide some solutions to you so that you were able to have something against which you can check your work after you've completed the exercise. And so here what I'm going to show you is my model. Now I'm not going to show you all of the columns that XLSX file for A320. What I'm going to do is just show you some of them and kind of the basic design pattern that you would be using while you're constructing a model. The model, of course, I asked for it to be in some serialization of RDF, like Turtle. This design pattern is not in Turtle. You would still need to convert this into a machine readable format and submit that, but you should be able to read off Turtle from this design pattern. So you should see some familiar faces here like RDF colon type or is subclass of, is have direct correlates into OWL or RDF space. And so from the top we have a GDC and we have a jet specification subclass relationship between that and GDC, so GDC being generically dependent continuous, and we have an instance of jet specification, and that is the Airbus 320N spec. That is the blueprint, as it were, for an Airbus 320N that will be falling under that column, or all those the attributes of which will be falling under the column. Now, this is an important distinction to make. What we're describing, what's being described in that XLSX file is not obviously specific Airbus instances. It is the specifications for instances that may be prescribed by the spec. And so we need to model the description of what those instances might be if they were to ever exist. Remember, we're trying to describe the data. We don't know if these things exist. We don't know if any Airbus 320N was rolled off according to these specs. What we do know is that the spec is about something, because it's information, and information has to be about something in BFO. Now what we don't want to say is it's about some specific instance that has like a jet engine part or is a fixed wing. So what we do is we use the is-about relationship, and we leverage some of the web ontology language logic, so OWL, by referencing only. And so what we say is that this Airbus 320N spec is about only something, whatever it is, that has all of these attributes hanging off of it. And it works just like this. It's about only the class defined as equivalent to the intersection of all of these attributes. And so I say class, but you'll note there's no little oval there that this is about only is pointing to. That's actually a feature of OWL. It's an anonymous class. We say it doesn't have a name. You can of course name these things, but there's no name associated with it. It's kind of like a hypothetical class. We're saying this Airbus spec is about this hypothetical class, which may or may not have instances, such that class is constructed out of these things over here on the right in this box that will represent the columns in that Excel file. So for example, it has a manufacturer, Airbus. It has a model FAA, and this is a string, so that I've asserted this has model FAA relationship or data type property into the string Airbus A320N or A320neo that you can see in the columns. Same for column E, except for BADA model. We also say that this, whatever this is, has continuant part of exactly 2 engine parts, jet engine parts, and it's a type of subclass of fixed wing. There are also these other attributes, some of which are data type properties like that have decimal values, like the length or tail height. And that's it. You kind of walk through identifying and extracting or constructing this anonymous class out of all these columns, and then building in or making explicit implicit information that connects columns to columns, even though they're not directly connected in the document itself or in that Excel file itself. What do I mean by that? Like, you may find yourself wondering how far you should go down in the modeling. Should I model just the jet engine as a part, or should I go out into the pistons or whatever Airbus specs prescribe? Well, what's in the columns? Well, first, do they stop there? Do they stop at jet engine or not? But you know, there's more to the columns though that you can reasonably pull out, and you can leverage BFO and that top level structure to help identify relationships between, you know, whatever the Airbus spec will be pointing to, if there is such an instance, and parts that it has. So at no point in the columns are you going to see a reference to continuate part or part of, but we know that this spec, the instance of this spec, will have a part in at least two, exactly two, and those will be jet engines. And that's how we start to make explicit the implicit relationships in that data. And we do that, and here's just a great example. So you don't have to model every single thing as fine-grained as you can all the way down to the atoms of the jet engine. You know, like that would be boiling the ocean, but you can certainly go beyond and should go beyond what's implicit or what's in the data itself, as insofar as you can extract some of the logical relationships across rows and columns in the data. There's column B. And I also wanted to highlight that you can say everything I just said in Protégé. So this is a screenshot from the Protégé editor. I have an Airbus A320neo spec 1. That's that instance of a GDC or a jet spec more specifically. And you can see that it's of a type is about only, and everything I just walked through in that design pattern, you can see reference there. And this is how you would write it. In Protégé, and you can basically hang off axioms of instances just like this, and so you can represent everything I just said in the same way. As a second case, we had same aircraft data file. You'll find a row for Airbus A320neo. It's designed to have a maximum not approach speed of 142. However, and this is where we're not just modeling the columns, we're going beyond the columns. I say, after 5 approaches, an instance has obtained an average maximum not approach speed of 139. Now, note, I'm not talking about just the spec anymore. I'm talking about an instance as well. And this one has been tested. Now, the plan here is for you to construct a BFO-conformant modeling reflecting this phenomenon. Start with that spec again. It is about only, you could flesh it all out if you like, but it's something that has a max approach speed knots of 142 decimal. It's also a subclass of fixed wing. And that's just the spec, that's just the information side. We say it's prescribing some anonymous class, as I said last time, but there is an instance that actually satisfies that class, and that's the instance that actually we're doing the testing on, and that's a fixed wing with this max, and it's prescribed to have this maximum approach speed. Now this instance of Airbus A320neo participates in a test process, and that's the overall test process, but it said there were 5, right? And so what we want to have is some big test process that has a bunch of approach test parts. And so we have temporal parts in BFO, temporal parts of this test process. All of those are processes. And these processes, these sub-processes, you might say, are measured by generically dependent continuous. Some information that's about the different approach parts, the different parts of this overall test process. Now, if we expand that out just a little, we could see, you'll see the processes on the right. In mice is a measurement information content entity. It's a type of generically dependent continuant that's specific to measurements. You'll see that we have the approach parts, all those 5 approaches. Those are the actual processes that are temporal parts of the overall test process. And you also have measurements of each of them. Now, those measurements have some measurement value, and they all use the unit knot. And knot is of an RDF type measurement unit, which you can find in a Common Core ontologies. But if you don't have that, it's not a big deal. I just want it for clarity here. Now, back over on the right, what we have is there's a test process, and there's a measurement of it. and it has some value 139, which is an integer, and it is a measurement information content entity, just like those measurements over on the left for each of the specific approach parts. And if you bring those all together, you might be asking yourself, John, how should I represent how do I represent averaging, like the process of averaging in the ontology? I'll say don't. You have measurement values. You can use Sparkle or some other query language or code to calculate and return the average of them. So what we have is a measurement of the average for sure. And we could of course explicitly represent that 139, but most often we have a bunch of information. We might want to generate an average. That average is something that would be is about the test process and has a measurement value 139. So we can kind of do it. We can do it as if we know the information 139, and we can just represent that explicitly, or we can, and I think this is the preferred approach, take the individual calculated or inputs to the calculation, run a Sparkle query, and return that average. Either way, this is the result. This is the answer. You have a bunch of processes, and so you have process with a bunch of sub-processes. Each of those has a measurement, some kind of measurement that's feeding into an average. The average being the average of the test, the overall test process for that aircraft. All right, so in the third case, we have a SOC structure definitions Excel file, and you'll find here 3 SOC title entries that mention Aerospace Engineer, and the plan was for you to construct a BFO-conformant model that reflects all 3 entries in their respective SOC definitions. This is the occupation code stuff I've been mentioning here and there, but as you can see, you have there's kind of a complicated structure that's involved in this occupation code. Is not really clear, like how they tease out Aerospace Engineers 172010 from Aerospace Engineers 2011. Of course, there's Aerospace Engineering in there too. They have this distinction between major groups, minor groups, broad groups, and detailed occupations. Here's some kind of general guidance on it. Major groups, here's their digits, categories, but they're very, major groups are very broad categories, and then minor groups are subcategories under a major group. Not very helpful. Broad occupations are groupings of related detailed occupations. Detailed occupations are specific job types. Honestly, not super helpful. Still not really clear, but I'll note that broad occupation and detailed occupation particularly confusing. I think I put this in here on purpose. You will need to learn to deal with confusing data. That is just the case. I've talked to people with the SOC community, and it is confusing to them too, so it's not just us. You should always research. So what I've got here is the link to the manual for SOC. It will help to some extent, but you should expect to encounter confusing data, and you should expect to have to research to figure out what the data means, and you should always not assume that you'll really have access to people, so you can disentangle or disambiguate. So, but here, for Aerospace Engineer, these are folks that perform engineering duties and designing, constructing, testing artifacts, and so forth and so on. Here's a characterization of them, one of the definitions. And so just pulling this characterization of Aerospace Engineer, what we're going to have is an SOC code, is generically dependent continuant. It's going to be about something. Again, this is that pattern again. It's about something. We don't know if there are actually any aerospace engineers. What we're doing is talking about a description of people who may bear a role, and if they exist, that role will be the sort of thing that is realized with acts of aircraft or aircraft design or adaptability evaluation or recommendation, being the output of equipment tests, the outputs of reports, or the output of aircraft specifications, etc. And so here's how you link. There's that anonymous class between the specification of the code itself and things that might fall under or in that class, and those having specific roles that can realize these various activities that are associated with the definition. And then the idea here being that you had that description, that information entity. If anybody gets a job as an aerospace engineer, they better have these qualifications and be able to engage in these sorts of realizations, because that's how it's defined. SOC1 code is about only that anonymous class, instances of which are bearers of some job role, which if realized or realized in these things. And say any equipment test is output of some act of equipment recommendation. All right, lastly here we have the employment wage file, and you'll find 3 OCC title entries that also mention Aerospace Engineer. And I wanted you to construct a BFO-conformant model, really, that reflects all 3 entries and all of their columns. Oof, it gets messy, right? But still, we have the SOC code. A lot of this can just be done on the information side. You have the SOC code, and you have different codes, or these different codes that fit under it, and a lot of them have just kind of literal values or text strings, like Aerospace Engineering and Operation Technologist and Technician, O Group, 99, 1235, and stuff like that. Blah blah blah. More annotations, not that interesting. Or is there? They all have the same area code, same own code. They have the same, well, 2 of them have the same O group, and 1 of them has a different one. Pretty interesting. Now, for you, this is just a little teaser. This is in the OCC title file. Go check the OCC codes in the previous file for the previous case and see if you notice anything interesting about the way these things are related. Now check this out. So we've got, for one SOC code, this is the Aerospace Engineering and Operation Technologist and Technician code. Note, there's some values associated with it. So total employment value, how many people are employed according to this code, or what we have is a total employment instance that's part of the SOC code, and it has a value 9,060, and then outputs of acts of measurement, which are processes about that total employment. And there's some kind of counting or count that adheres in some population, and that total employment measurement is about that count. There's a population bearing equality, which is the input to an act of measuring that in turn outputs a total employment information, which has a count of 9,060, and is continual part of the SOC code. And that, in a nutshell, is a modeling for all 4 tasks. And I hope you had an easier time than I suspect you did modeling this information. But, in the interest, it was in the interest of pain. So hopefully, as easy as it was, or as hard as it was, you felt the pain, and now you are fully motivated to work with me to create automated solutions to do exactly this sort of modeling at scale.